So, hello everyone. I am Gitanjali Jaina. I am a PMRF TA for this course, which is Physics of Linear and Nonlinear Optical Wave. Right. So, this will be the last live session for this course. So, I will try to cover the I will try to cover the concept, whatever that has been taught in this last week, which is basically mostly about solitons. What is the how the pulse evolve in the presence of any dispersion or in the presence of any non-linearity, or how it behave when we have both, like both dispersion as well as non-linearity in the medium. Okay, so let me start from our first question, which is, so we'll start from simplest question, then we'll gradually move towards the more the most difficult one. So this question, it's based on the solitons. So it says, say fiber has a nonlinear coefficient gamma, which is 3 watt inverse and kilometer inverse, and the GVD means the group velocity dispersion. I think all of you know. GVD parameter, it's already given. Beta 2 is minus 30 picosecond square per kilometer. And for this solitons, it's also given the pulse width, which is T0 is 2 picosecond. And the question asks to find out what is the peak power, which is P0, required to form a fundamental soliton in the system. So solitons, they are lower order solitons as well as there are higher order solitons. So based on the parameter n, which is the soliton order. If you recall, there was a parameter defined in the class, which is the ratio of the dispersion length to the nonlinear length. So it basically defines what will be the type of soliton that will be propagating in the fiber. Okay, so for fundamental soliton, what we have, the condition is n should be equal to 1. So let me, okay. So for fundamental soliton, so the question asks what will be the peak value of power, which is P0 for a fundamental soliton. So for fundamental soliton, we have n equal to 1. So which means this will be, so LD should be equal to LNI, right? Because it's the ratio of LD to NI for n equal to 1. And if we recall, LD is nothing but it's the dispersion length for the fiber, and it is given by the ratio of uh, T0 square over mod of beta 2. This is for the dispersion length, and for the nonlinear length, we have it's the inverse of gamma P0. Gamma is the nonlinear coefficient, and P0 is the peak power. So if you equate both the sides, is T0 square mod beta 2, which is equal to 1 by gamma P0. So that means we want what should be the value for P0 such that n equal to 1. Then for this, P0 should be mod of B2 over gamma T0 square. So all of these parameters, it's already given for the fiber. Like beta 2 is already given, it is minus 30 picosecond square per kilometer. So it's a anomalous dispersion region. So beta 2 is negative here, and gamma is also given. It is 3 per watt kilometer. And what else? T0 is also given, which is the pulse width, which is 2 picosecond. So that means P0 now we have, if we take these values, P0 is 30 over P4. So this will be 2.5 watt. So this much amount of power it is required to support the fundamental soliton when we have the beta 2 which is minus 30 and the nonlinear coefficient which is 3 per watt per kilometer. So this is the one of the simplest question. So let us move to our next problem. So the question says a pulse has the following parameters, which is temporal width, it is given 1.5 picosecond, peak power P0 it is given 8 watt, propagates in an optical fiber with the GVD coefficient, which is beta 2 is minus 18 picosecond per kilometer. Nonlinear coefficient is also given. And the question asks what is the dispersion length, soliton order, and what is the nonlinear length of the fiber. So for this fiber, we are given that the pulse is pulse width 1.5 picoseconds. Peak power is 8 watt. Propagates in optical fiber with CVD coefficient beta 2 is minus 18 picosecond square per kilometer. And it's also given gamma is 2.5 per watt kilometer. So dispersion length we have seen before, it is given by T0 square over mod of beta 2. So T0 square is the pulse width. Here it is 1.5 picosecond square, and beta 2 is 18 picosecond square per kilometer. So this will be 0.125 kilometer. And the second thing is to find out, let us first find out what is the nonlinear length, because soliton order is nothing but the ratio of dispersion length to nonlinear length. So for nonlinear length, we have it's the inverse of gamma P0. Gamma is already given, it is 2.5 watt per kilometer, and P0 is it is 8 watt. So this will be 0.05 kilometer. So now we have calculated what is the value of LD and LNM. And for the soliton order, we need it is square root of LD over LNM. So LD is it's 0.125 kilometer, and LNL is 0.05 kilometer. So this will be square root of 2.5, which will be around 1.58. So the soliton order for this case is 1.58. So here we can see the value of in the soliton order, it is greater than 1. So that means it is no longer a fundamental soliton. It's correspond to a higher order soliton. when n is greater than 1. So, and for this type of soliton, we'll see a periodic exchange of periodic reshaping of the pulse when it propagates through the fiber. When n is greater than 1. When n equal to 1, then the the nonlinear effect as well as the dispersion, they try to compensate with each other so that the pulse wave doesn't get affected when it propagates through the fiber. But for this case, we'll see there is a periodic reshaping of pulse when it propagates through the fiber. Okay. So let us move to our next problem. So next problem, it's also a simplest one. Um, it's given for lambda equal to 1550 nanometer and A effective is 50 micrometer. And it's also given the nonlinear refractive index N2 is 2.6 into 10 to the minus 16. And with the value of L dispersion is 202 kilometer. So what is the peak power of the propagating soliton inside the fiber? So we need to find out what is the value for P0. Let us see. So for P0, L dispersion is given, right? It is 202 kilometer. And if you take it's a fundamental soliton, so as long as it's not mentioned, we can take it as a fundamental soliton, sorry. So for this, n is 1, and we can equate LD with ln. So 1 by gamma P0 should be equal to T0 square by beta 2. So that means P0, it's beta 2 mod by gamma T0 square. So uh, in the question, it's given the A effective. So gamma is not given directly, but if you recall, the expression for gamma is K0 N2 over A effective. And K0 is nothing but 2 pi over lambda 0 N2 A effective. So that means now you can write E0 as beta 2 over T0 square. We can take this is 1 by dispersion length, and gamma is 2 pi N2 lambda 0 A effective. So now we have expressed the peak power in terms of the parameter that is already being given in the question. So lambda is given, it is 1550 nanometer. And lambda 0, sorry, A effective is given 50 micrometer square. And 2 pi into is 2.6 10 to the minus 16 centimeters square. This will give minus 4, and there is 202 kilometer. So this will come around a value of 2.35 microwatt. If I am not wrong, this will give a value. So let me check. So this will give a value of 2.35. Okay, so let us move to our next problem, which is also a quite easier one. So it's just some of the parameters given and we need to find the unknown parameter. Question is consider P0, which is the peak power of the pulse. It is given forward and beta 2 is given, which is minus 24 picosecond square per kilometer. Nonlinear coefficient gamma is given, which is 2 per watt per kilometer. And the question asks what should be the temporal width, which is T0, that will allow propagation of fundamental saluton. So, as I said before, for fundamental saluton, we need n should be equal to 1. So, that means the value for LD should be equal to L and L. And we need to find out what is T0. So, this will give T0, T0 gamma over beta 2, which is equal to 1. So T0 square is beta 2 gamma B0. So let us put the value first. T0 is it's given 24 and gamma is given it is 2. P0 is given it is 4. So that means T0 it's square root of 3 and the unit will be picosecond, which is 1.732 picosecond. So let us move to our next problem, which is a bit different to what we've seen in the first four problems. So please go through the question once. Question is an optical pulse with an initial amplitude A0 is 2, 2 square root of kilowatt propagates through a nonlinear curve medium with gamma is given 2 into 10 to minus 3 per watt per meter. So calculate the phase shift after propagating a distance of z equal to 5 meter and what will be the final amplitudes. So nonlinear coefficient is given and we need to find out what is the phase shift. So recall when we have a curve medium where chi3 is non-zero because if you recall for fiber the value for chi2 is 0. So the dominant contribution for the nonlinear effect where it will come from the chi3. So this will give rise to the optical Kerr effect. So that's why we mostly deal with the optical Kerr effect whenever we are talking about the fiber. So in the class, it's if we assume that inside the Kerr medium we have zero group velocity dispersion. So that means the beta 2 value it is 0 or it is negligible. Then the nonlinear Schrodinger equation simplifies to dou A by dou Z equal to I gamma A square A. So A is ZT, which is in the class it's given you ZT. It is a slowly varying envelope of the optical field and gamma it's the nonlinear coefficient. And whenever we have this kind of medium, that is when the GBD is zero, so beta 2 is zero, then we have seen in the class that the in the amplitude of the envelope it will remain unchanged. So whatever the value was before, it will remain as it is. So it will be unchanged since no loss or GVD is no GBD is present. So for this type of we have seen a solution like AZ is A0 e to y I gamma A0 square Z. So this is nothing but the phase, which is the imaginary part of the exponential. So I5. So after propagation, A0 will remain as it is. But the phase phi of Z, if we take that the initial phase is 0, then the total phase after propagating distance Z, it will be gamma A0 square Z. So this is the nonlinear phase shift. We can see here the phi of Z, it is directly proportional to Z. So that means it is whenever ZVD, so it's the condition, this equation it's only applicable whenever we have zero ZBD in the system. If it is not zero, then the expression will be different. But when ZBD is zero, then we can say phi of Z will have this type of expression. And for this case, the phi of Z, it will vary linearly with respect to the distance Z. And it also depends on the amplitude of the pulse by the square of the pulse amplitude. So if we change the pulse amplitude, then it will vary as a square of the pulse amplitude. So this is what we have seen in the class. It's corresponding to the self-phase modulation. And okay, so our main task is to find out what is the phase shift after propagating a distance of z5 meter. So we are given already given a0, which is the amplitude and the nonlinear coefficient. So gamma, a0 and z, these are already given. So gamma is 2 into 10 to the minus 3. A was given, it is 4 into 10 to the minus 3 square root A0 square, only 4 into 10 to the minus 10 to the 3, and distance is 5. So this will come around 40 radian. Okay. Okay, so let us move to our next problem. So the next problem says there is two co-propagating continuous waves with amplitude A1 is 2 and A2 is 3 enters the curved medium of the gamma, which is 1.5 into 10 to the minus 3, and length it is given 10 meter. So the first part of the question it asks what is the individual nonlinear phase shift for each waves, and in the B part, it says consider a situation when we interfere these two waves at the output. Then what should be the resultant intensity and what will be the total phase difference? So instead of a one propagating wave, single propagating wave, we have a co-propagating continuous wave, which is being launched into the nonlinear medium, which is the nonlinear coefficient gamma is given 1.5 to 10 to the minus 3 per watt total inverse. Length it is given 10 meter, total length of the fiber, and A1, A2 of the two co-propagating wave is also given. So to calculate the individual for phase shift, what we need gamma A1 square and the total distance L. So that means this will be all of the parameters is already being given in the question. So 1.5 into 10 to the minus 3. A square is 4 to 10 to the 3 and L is 10 meter. So this will be 60 radian. And for the second wave, phi 2 is gamma A2 square L. So gamma is 1.5 to 10 to the minus 3. A2 is A2 square. So this is 9 into 10 to the minus 3. And this is 10. So this will be 135 radian. So finding the phase, individual nonlinear phasing, this is easy. Now next what we are doing, we are interfering this two co-propagating mode so that they will interfere and the intensity will be a vector sum of the individual intensity. So to find out the intensity, we have A total in the output is A1 e to the I51 plus A2 e to the I52. So intensity will be the square of the amplitude. It's directly proportional to the square of the amplitude. So we can find out a rough value for the intensity. The exact expression will be done by taking the constants also. So let us say the constant is 1 for this case. So this is equal to square of A total, which will be A1 e to the I51 plus A2 e to the I52 square. So this will give A1 square plus A2 square is 2 mod A1 mod A2 cos phi 2 minus phi 1. So mod A1 square it will be 4 into 10 to the 3. So let us just consider the leading digit. Unit will be same for all the cases. It will be 9 plus 2 to 3 kilowatt cos. Phi 2 is we have already calculated. Is at the output it is 135 and it is 60. So pi 2 minus phi 1 will be 75 radian. So this will be the resultant. intensity at the output of the fiber. Okay. Okay. So let us move to our next problem. Now we'll start a more difficult question. So previous 4 to 5 problems, these are all based on the direct implementation of the formulas. If you know the formula, then you can easily find out what is the what is the soliton order, what is the peak power, and the other parameter. So now we'll see more difficult question. So the question says, in a soliton communication system, it is operating at the wavelength 1.55 micrometer by using a dispersion shifted fiber with D is given 2 picosecond per kilometer nanometer, and the effective area of the core of the fiber, it is also given 50 micrometer square. So the question asks to find out what is the peak power, which is P0, what is the pulse energy required for launching fundamental soliton into the fiber. And it is also telling to assume hyperbolic secant pulse with a full width half maximum of 30 picosecond. And take into is 3.1 into 10 to the power minus 17. Okay, so we need to find out what is P0 first. So it's given it's a fundamental soliton, that means N is 1. So LD is N and N. So I'm writing this equation again and again so that you can easily recall whenever you are going through a question, you can really easily recall the what was the equation, what was the value for fundamental soliton. Okay, so LD is 1 by gamma P0, and sorry, LD, it is P0 square by beta 2. So LD is T0 square by beta 2, and LNL is it is 1 by gamma P0. So that means for P0 we need gamma value T0 square and beta 2. And if you see the question, this parameter it's not given directly. So we need to find out what is the value for the parameter by using the known parameter. So let us say gamma, it is not given, but if you recall the expression for gamma is, so let us first find out T0 first, because okay, the pulse width at full width at half of maximum it is given, it is 30 picoseconds. So that means T0 is not given. T full width at half maximum it's given, it is 30 picosecond. So that means for second type of pulses, you can easily find out T0 from the T full width at half maximum by dividing it by a factor 1.763. So this is only for the second pulse. So when we have a Gaussian pulse, then this factor is different. This will be 1.665. But when we have a second pulse, then this is 1.763. So please care whenever you are finding the pulse width for a different type of pulse, please be careful while taking the constant in the denominator. Okay, so for this question, it was given the it says second pulse. So okay, so pulse width it is full width at half of the maximum. It's already been given. This value is 30, I think. 30, and this is 1.763. So this will come around 17 picosecond. So we calculated what is the value for pulse width. Let us now calculate what is the value for beta 2. So beta 2, if you recall the previous lecture, I think in week 4, we have seen what is the expression for beta 2 in terms of the dispersion parameter. So this is given by lambda square d over 2 pi c. So lambda is given, it is 1.55 micrometer, and d is also given, it is 2 picosecond per kilometer nanometer. So that means if we now calculate beta 2 now, so beta 2 will be lambda square, which is 1.55 into 10 to the minus 6 square. D is so 2 picosecond per kilometer nanometer. So let us change the nanometer to meter. This is 10 to the minus 9 and 2 pi C is 3 into 10 to the power 8 meter per second. So this will give second. You can convert it to picosecond by multiplying a factor 10 to the minus 10 to the 12. So this will, so okay, let me calculate it first. It is 1.55 into a minus 6 square to picosecond per kilometer, and this is 10 to the 12 whole divided by 2 into 3.14 into 10 to the 8. So this will come around 2.55 picosecond square per kilometer. So now we know beta 2 also. So let us calculate what is gamma now. So gamma will be K0 N2 by A effective. So K0 is given. Okay, it's not given. Can take this is 2 pi over lambda N2 effective. So 2 3.14 N2 is 3.1 into 10 to the minus 17. 3.1 into 10 to the minus 17. And lambda is 1 point. Instead of calculating this again, we can directly put it here so that we can easily find out what is P0, which we require. So P0 will be lambda B2 A effective 2 pi into T0 square. Okay. So lambda is 1.55 micrometer. Beta 2 is 2.55 picosecond square per kilometer. Um, and A effective is given, I think, 50 micrometer square. 50 micrometer square, which will be minus 12 meter square, where there is a value meter. And we have 2 3.14 and 2 is 3.1. into 10 to the minus 17 meters square per watt. So I'm just writing the units also because so that the final value will be the exact way. And we have T0 square, which is 17 picosecond. So 17 square. Picosecond square will cancel here. And there is meter square here, which will cancel with this one. And if we take kilometer to into a 3 meter, then this will also cancel. So we have the unit in terms of watt. Now the final value will be, so let me recheck whether the answer is correct or not. 1.55, 6, 2.55, 50, 3.14, 3.1, 17 square, 10 to the 3. So this will give a value of 3.51 into 10 to the minus 6 watt. You can write it as microwatt. So we know P0 now, which the question was asking about. Now for the pulse energy, we just need to take the integration. So E pulse will be integration of Pt dt. So Pt you can write it as P0 and second pulse dt. So this will give a value of 2 times P0 T0. So P0 T0 value we already know. We have calculated the value for P0. This is 3.51 10 to a minute. Mm, mm, then why it is waiting here? Okay, now it's fine, I think. So this is still behaving strangely. So this will be 10 to a minus 6. Mm, what is happening? Let's see. Okay, so if we write it here, 2 into okay, 2 into okay P0 it's 3.51 into a minus 6 and T0 it is we have calculated it. It was 17 picosecond. 17 picosecond, which is 10 to the minus 12. So this will give a value of 1.1934 to 10 to the minus 16 joule. Okay. Okay, so let us move to our next problem. So the question says consider a sinusoidally modulated pulse envelope at the input end z equals 0 of the curve medium. So A0t, its pulse envelope it is given to us. A0t is A0 1 plus 0.5 cos 2 pi t over t, where A0 it's given, A0 value is 1 square root of what, and Tm it is given 2 picosecond. This is the pulse width. And the question says the pulse is propagating through a curve medium with length L equal to 1 kilometer, and the nonlinear coefficient gamma it's also given. Find the analytical expression for the envelope AZT after propagation. Then and calculate what is the phase of AZT at t equal to 0 and t equal to 1 picosecond after traveling a distance of 1 kilometer. So, to calculate what is the phase, we need to find out what is the square of the amplitude, because the amplitude will remain same during propagation. If the CBD is 0, then we can say this is A0 square 1 plus 0.5 cos 2 pi t by t square. So this you can write it as A0 square 1 plus 0.25 cos square 2 pi t by t plus 2ab. So this will give a value of cos 2 pi t by t. So we can further simplify this cos square function. So this will give A0 square 1 plus cos 2 pi t by t, and this will be cos square will be 1 plus cos 2 theta cos 4 pi t by t. So that means we have, this is A0 square 1. So there will be 0.125 here. So this will give 1.125 plus 0.125 cos 4 pi t by t and cos 2 pi t by t. So that means the envelope, you can write it as, or the envelope at a distance z, this is AZT, which is nothing but A0t exponential I gamma Z A0t square. So this is the phase that the pulse will have after propagating the nonlinear medium. Okay. So for completeness, you can write it. This is as A0. Um, A0t was given this expression 1 plus 0.5 cos 2 pi t by tm. This is A0. And the phase part is exponential I gamma A0 square Z 1.125 plus 0.125 cos. So we can put 2 picosecond here. So this will give 2 pi t plus cos pi t. So this will be the phase envelope when it propagates through the medium. For phase, we need to phase calculation at z equal to 1 kilometer when the time t is 0. So phi of zt, you can write it as, so whenever the group velocity dispersion is 0, we can say phi is gamma z a 0t square. With this, we have already found out what is the complete expression. So gamma, it's already given in the question. It is 5 watt per kilometer, and z is given 1 kilometer, and a 0 it was given 1 square root of half. So 5 z 1 kilometer, and when the time t is 0, it should be 5 1.125 plus cos 0 plus 0.125 cos 0. So we put t equal to 0. This will give a value of 11.25 radian when the time t is 0. Now when the time increases to 1 picosecond, this is 5 1.125 plus cos pi 0.125 cos 2 pi. So this will be 1.25 radian. Okay. So you just need to remember what is the expression for nonlinear phase shift whenever we have a group velocity dispersion of 0. Okay. Okay. So next problem, it combines the concept of week 4 as well as week 12. Okay. So I have put it in the given question because it will revise your concept as well as it will correlate the expression that we have seen before, how the and the expression that we are seeing now. Okay. So please, okay, let me read out the question first. It's given, consider a Gaussian pulse with spectral width delta lambda 0, 3 nanometer. So it's a bit long question. So please try to cooperate with me. It will cover all the concept. Okay. So delta lambda 0, it's 3 nanometer, and it propagates through a material with a refractive index given by n lambda 0 is this expression. Okay, so let me write side by side. So we are given the refractive index variation as a function of lambda 1.48 plus 0.0015 lambda square minus 0.005 lambda per 4. So lambda, the range is from 0.7 micrometer to 1.9 micrometer. So in the first part of the question, it is asking what is the calculate the material dispersion coefficient dm at lambda 1.5 micrometer. In the second part, it is saying if the medium can be treated as a linear medium, then what is the pulse width of the initial pulse, which is with initial width 2 picosecond after traveling a distance of 8 into 10 to the 5 kilometer through the dispersive material by considering that the group velocity dispersion beta 2 is non-zero. Okay, so first part we need to calculate what is the material dispersion. So let us see. For material dispersion, recall dm, it is given by minus lambda by c d square n over d lambda square. So it is related to the second order derivative of n with respect to lambda. So n of lambda is given. You can easily find out what is the value of dn over d lambda. Is 0.005. So that means dn by d lambda. This will give minus 0.003 lambda cube plus 0.00. So the next derivative, this will give 0.009 lambda 4 minus 0.001 lambda 6. So we need to find out what is the value for dm at lambda equal to 1.55, which is the operation wavelength. So d square n over d lambda square now will be 0.009. So it was given 1.5, I think. Yes, 1.5. 1.5 to our 4 minus 0.001, 1.5 to our 6. So this will be 1.69 10 to a minus 3 micrometer per units. Okay, so now we can calculate what is the value for dm. dm is lambda by c 1.5 by c, which is 3 into 10 to the power 5 kilometer per second. This is 1.69 10 to the minus 3. Okay, we can convert it to picosecond. So this is just to get Tm in terms of picosecond per kilometer nanometer. So this will give minus 8.45 picosecond per kilometer per nanometer. Okay, so we have found out what is the value for Dm now. For now, we need to find out what is the temporal width. What is the change in the temporal width whenever we consider that the medium is a non-linear medium? Sorry, it's a linear medium, but the beta 2 is not 0. So this is equivalent to saying that we are treating a linear medium with 0 value of beta 2. Okay, so please recall for to find out the temporal width. So we have seen in, I think, week 4, that if we have a pulse like this, let's say we have a Gaussian pulse. Like this, which has a width of t0 and the maximum is this is psi 0. Let us say this is a form psi 0 e⁻ minus t square by t0 square. So let us say this is of this form. So when it propagates through a medium with non-zero value of beta 2, we have seen that the amplitude will get affected as well as the width will also get affected. So there will be decrease in the amplitude as well as increase in the temporal width. So this is now the new value for the temporal width, 0 prime, and this is the new value of the amplitude. So we have seen temporal broadening for this case. And the expression is like, okay, the variation is like when we move through the fiber, the amplitude will decrease. axis amplitude for the fiber. And for the same, for the temporal width, it will increase as we move through the fiber. So T0 is the initial width and T0 delta is the new width due to non-zero values of beta 2. And what was the expression we have seen before? Psi 0 prime. So this has been derived in week 4. Please revisit the expression. So I will directly write down what is the final expression. So psi 0 prime, you can write it as psi 0 1 plus 2 beta 2 z by t0 square. Uh, and for temporal width that we need to find out in this question, T0 delta will be initial width 1 plus 2 beta 2 z by T0 square. Wow. So this is only for the case when we have a Gaussian wave of form, which is a form like this, that is in the order of minus t square by t0 square. So if it is different form, like if it is any constant value, then this there will be a renormalization in the expression will be same, but there will be some constant which will be get divided in the final expression. Okay. And if you now relate the previous, this is what we have seen in week 4. Now, in this week, we learned that the dispersion wavelength, which is LD, it is given by T0 square by beta 2 more. So, this is the distance over which the pulse broaden, significantly due to dispersion. So that is why this is the dispersion wavelength. So now we can change the expression here in accordance to whatever we know from this way. So that means you can write T0 delta, which is the final pulse width, as T0 1 plus 2 beta 2 Z square over LD square. Whatever. So if you are given the final the fiber length and what is the dispersion length, then you can find out what is the value for the final pulse width. Okay, so this is the final pulse width and T0 is the initial pulse width. And this is only, this expression is valid when we have beta 2 is non-zero and other values of the dispersion is negligible, like beta 3, beta 4. And when we have gamma is 0, that is it's a linear medium. Okay. Okay, so let us see what is being given in our question. So T0, I think it's already given 2 picosecond. LD we can, I think, calculate it. LD is, so LD is 20 square by beta 2, right? So we need beta 2 for our case because Z is known, it's already given. Let us see what is given. Z is, okay, 8 into 10 to the 5. This is 8 into 10 to the 5. T0 is also given, it is 2 picosecond. But we don't know LD, which is T0 square by beta 2 mode. So then That means we need to find out beta 2 first so that we can calculate the temporal. Okay, but what we do know, beta 2, whatever the parameters is given, it's not easy to find out. But in the first part, we have seen what is the value for the material coefficient, material dispersion coefficient, that is DM. This we already have calculated it. Okay. And if you recall, there is a relation between beta 2 and DM. So if you take the ratio beta 2 over DM, this will be nothing but minus lambda square by 2 pi c. So that means we can easily find out beta 2 as minus lambda square 2 pi c dm. All of the parameter is known now. This is 1 point. Let me see. That is, so dm is 8.45. Lambda is 1.5 micrometer. So this is 1.5 micrometer square. This is square 10 to minus 12. dm is 8.45 picosecond. 234.14 3 into 10 to the 5 kilometer per picosecond. To 10 to the minus 12. So this will give 1 into 10 to the minus 5 picosecond square per kilometer. Okay. So now we know what is the value for beta now. Okay, sorry for this. So that means LD, the dispersion length. This is T0 square over beta 2, which is 2 picoseconds square. Beta 2 is 10 to the minus 5. So this will give 4 into 10 to the 5 kilometer. Okay. So that means if you now calculate the constant, which is 20 square, 2z square by LD square. So this is nothing but 4 into z, z square, which is 64 into 10 to the 5 means 25. LD square is 4, 16 into 10 to the 25. So this will give 16. So T0 delta now is T0 1 plus 2z square by LD square of, which is 2, 1 plus 16 to power half. So this will be 8.25 because, okay. So this will be the final answer. This will be the final width when you travel through a distance of 8 into 10 to the 5. Okay. So is this problem clear? Or do you have any doubt in any of the steps? If not, let us move to our next problem. Okay, let us move to our question number 10. So please go through the question once. This question is related to question number 9. Okay. Okay, so the question says consider a Gaussian pulse of width 10 picosecond. It is propagating in a linear dispersive material with d square k by, so beta 2 is given. That means d square k by d omega square at the operating wavelength 1.5 micrometer. Then what is the pulse width of the Gaussian pulse after traveling a distance of 5 kilometer and 10 kilometer along the length of the fiber? So ignore all the higher order derivatives of beta. Okay. So we have seen in the previous question that if we have a pulse like this, if you have a Gaussian pulse of psi 0, it was minus t square, t0 square, it were minus omega 0 t. So let's say we have a pulse like this. For this case, for this type of pulse, we can write the temporal width, the final temporal width. This is t0 delta. This will be t0 1 plus 2z square LD square to power half, where LD is t0 square over beta 2. And it is also given t0 is 10 picosecond and beta 2, it is nothing but t square k by d omega square. It's also given it is 3.54 into 10 to the minus 26 seconds per meter. So that means you can easily find out what is the value for LD, right? So can you please calculate and let me know the answer? So LD will be nothing but T0 square over beta 2. So what will be LD for this case? Okay, if it is taking time, so let me write down the answer. So this will come around LD is A0 square by beta 2. So this will be 10 picosecond square. So 10 is 100 into 10 to the minus 24 over beta 2 is 3.54 into 10 to the minus 26. So this will give a value of 2.825 kilometer. I am not wrong. So this is 2.825. Yes. Okay. So now we know LD. So we can find out what is T0 delta, which is, let's say, for Z equal to 5 kilometer. So this will be T0 1 plus 4 Z square by LD square. So T0 given it is 10 picosecond. So there is a half here also. 1 plus 4 Z square will be 25. LD square will be 2.825 square. And this width will come around 36.78%. For the second one, it's easy. You just need to put the value for set now. For T0, 5 is done. For 10 kilometer, this will be 10. 1 plus 400, 2.825 square. So this will be 71.5 because. Okay. So for this type of pulse, we have seen we can easily find out what is the temporal width when it propagates through a dispersive medium, which is also a linear medium. Okay. So let us move to our next problem, which is based on the spectral width. Please go through the question once. So in the question, it is given, consider a chopped Gaussian pulse of the following form. And it was asking to calculate what will be the expression for the spectrum A of omega and what will be its spectral width at which the intensity becomes 0.3678 times of its maximum value. So we are given psi z equal to 0 t, which is c e to the power minus t square t0 square 1 plus I gamma e to the power I omega 0 t. So to find out A of omega for this type of spectrum, so we need to do the Fourier transformation. This is A by taking Fourier transform psi z equal to 0 t. And this is A of omega It will be 1 by 2 pi integration psi 0 t e to power minus I omega t dt. So just put the value for psi 0 t. We can get this is 1 by 2 pi minus infinity to infinity. This will be c. So there will be a c here. E to power minus t square by t 0 square 1 plus I gamma e to power I omega 0 minus omega t dt. So this is the well-known integration that we have seen most of the cases. Okay. So this is nothing but is the form of minus infinity to infinity e to power minus alpha t square plus beta t. What is alpha here? Alpha is nothing but 1 plus I gamma over t0 square. And beta is omega 0 minus omega times I. So the integration of this will give, so this integration will now become c by 2 pi root over of pi by alpha e to 1 beta square by 4 alpha. So just put the value for alpha and beta. So this is 0 square root pi 1 plus I gamma and it were beta squared. So this is omega 0 minus omega square over 4 alpha 4 1 plus I omega. So this is the spectrum A of omega. So C of T0 2 root pi 1 plus I gamma of e to power minus T0 square omega 0 minus omega square by 4. So we know the spectrum now to find out what is the value for the intensity. So intensity is, it is directly proportional to the square of A of omega, right? So this will be equal to, so just put the value of A of omega that we have calculated before. 1 plus A omega to the power e to power minus T0 square omega 0 minus omega square by 4 1 plus I. So if you find out, this will give a value. If you take the complex conjugate and find out the exact expression, this will be c square t0 square 4 pi 1 plus gamma square e to power minus t0 square omega 0 minus omega square 2 times 1 plus gamma square. Okay. So this will be the intensity expression. And to find out at which frequency, what will be the spectral width such that the intensity is 0.3678 times of its initial value. So we need to equate. So let us say for a frequency delta omega, we have the value, it is the maximum value times 0.367. So this is nothing but the 1 by E value. So if you calculate it, it is 1 by E value. So that means now just use the constant term will cancel both sides because maximum value is this much, right? So this will be exponential minus t zero squared, and omega 0 minus omega is nothing but delta omega square, right? Over 2, 1 plus gamma square is e to r minus 1. So this will be a 0 square delta omega square to 1 plus gamma square is 1. So you just have to rearrange it to get the value for what will be the value for delta. So this will give square root to 1 plus gamma square over t0. So last two and three expression, so from where, like up to this, is it clear? So let me know we are up to which step here. It's not clear to you. Let me know whether up to this it is clear or not. E omega squared expression. Okay, for the intensity, right? Okay. So this is, so you have already calculated what is the value for the E of omega, right? So you just need to take what is the sorry mod of A of omega square, which is nothing but this expression we have already seen with. So to find out this is the final expression that I have directly wrote down, but you can get it by taking, so A of omega square, it is nothing but A of omega A star omega, right? So for the exponential part, you can see there is a 1 plus I omega here. So that means you can multiply um, 1 minus I omega. So in the denominator, we have now 1 plus I omega, 1 minus I omega, right? So this is just to take the complex conjugate so that this expression will be easier. So in the upper part, we have omega 0 minus omega square 1 minus I omega divided by 4, 1 plus gamma square. And if you take the square of this, so this is only for one term. If you take the mod square, this will be t0 square omega 0 minus omega square 1 minus I omega, and the complex conjugate part will be 1 plus I omega. right? So this will cancel, right? So only we have t zero square omega zero minus omega square by 2. So there will be t zero square here also. Okay, so let me write it over. So we have this part, and the complex conjugate of this will be t zero square plus 0 minus omega square. Sorry, this part will cancel, right? So only we have the final expression is, okay, there will be 4. Mm-hmm. If omega square 4 1 plus gamma square. I think I'm missing out something here. Okay, so there is 1 plus gamma square. Yes. Then it will cancel from the denominator. Oh, I'm not getting what you are saying. But okay, so you mean I think, so in the exponential, so you are telling about the exponential part, right? In the exponential, we have minus t zero square omega zero minus omega square over 4 alpha. This will cancel the numerator. Mm, I don't think so. Or so I'm just multiplying here. So as you said, I'm just multiplying 1 minus I omega here and 1 minus I omega here. Okay. So this will give exponential t zero square omega zero square 1 minus I omega 1 plus gamma square. So is this expression clear, or is there any mistake here from my side? Okay, please go through it because this is, I think there shouldn't be any doubt here because multiplying with 1 minus I omega here and 1, but there is no 1 plus I omega in the numerator. So that means there won't be any cancellation according to me. Okay, let me see whether uh, the steps are, but the final expression, it's right. It will be C0 T0 square, this expression. Okay. The rest is just, it's straightforward. So we need to find out what is the delta omega such that the intensity, it's 1 by of its initial value. So that means this value, it is equal to 1. So we can find out what is the spectral width. It is square root 2 1 plus gamma square by T0. Okay. Okay. So let us move to our next problem. So the question says, for the Evo pulse, psi z0t, which is given by this expression, what is the total phase acquired by the pulse when it propagates through a nonlinear fiber with chi3 not equal to 0 and chi m equal to 0 for m greater than 3. And consider that the group velocity dispersion is 0. For the phase, what we need, so it's given psi 0t c to power minus t square by t0 square 1 plus I gamma e to power I omega 0t. So what is the initial phase? Initial phase is nothing but what is the imaginary part of the exponential. So imaginary part, it is omega 0t minus gamma t square by t0 square. Right? So this is the initial phase that we have. Now when it travels through a distance, we have pi nl, which is gamma psi 0 square z, which is z gamma c square and c to power minus 2t square by t0 square. Okay. Mm, mm. For total phase, what we need, this is nothing but phi is pi nl plus phi 0. So which is omega 0 t minus gamma t square by t0 square plus z gamma mod c square e to power minus 2t square by t0 square. So this is the total phase. In the next part, it is asking to find out what is the instantaneous frequency of the propagating wave. So for instantaneous frequency, so we know the phase, so we can take the time derivative to find out what is the instantaneous frequency. So this is d by dt of omega 0 t minus gamma t square t0 square plus z gamma c square e to power 2t square by t0 square. So this will give omega 0 minus 2 gamma t0 square plus d phi nl by dt, where this is, if you take the derivative, it will come minus 4 gamma c square tz e to power minus t square t0 square by t0 square. Okay. So first you need to find out what is the phase, then you can find out what is the angular frequency or the instantaneous frequency. Okay, so let us move to our next problem. Next problem is quite easy one. It is similar to what we have seen in question number 1 and so please go through the question once and let me see whether it is easy for you or you want me to calculate. So this, okay, let me just quickly go through the solutions. It's given it was asking about what is the A effective. Okay. So A effective, we need to find out and we are given P0, which is nothing but mod of beta 2 by gamma T0 square. Beta 2 is the group velocity dispersion coefficient and gamma is the nonlinear coefficient. And as I said before, T0, you can write it as, so if it is not given a, it's not given a uh, second pulse, right? So you can take this is a Gaussian pulse. So for Gaussian pulse, we know the relation between T0 and to FWH. This is, if you divide this by a factor of 1.665, then you can find out the, so it is given, oh, okay, it's already given, it's a Gaussian form. So this is 10 picosecond, 1.665, which will be 6 picosecond. So now we know T0, right? And we are also given what is the value for D. So that means we can easily find out what is beta 2 now, because beta 2 is lambda square D by 2 pi C. So lambda square is 1550 nanometer square. Just put the value for the whatever is given, and please keep in the mind what is the units you are taking into. So if you want to calculate in terms of second square per meter, it will come around 2.04 to 10 to the minus 23 second square per meter. So we know beta now, so we can calculate gamma also, which is beta 2 by T0 T0 square. Beta 2 is K0 and 2 A effective. So this will be 2.04 10 to the minus 23 25 10 to the minus 3 6 square is 4. So from this, because n2 is also given in the question. So if you just put the value, this will come around 5.17 minus 15. Okay. So this is the, I'm just writing the final value. I think in the previous, the confusion may be arising while taking the exponent, sorry, taking the complex conjugate. So if you see it like this, like, I think whatever you are thinking about, as far as I can guess, so you are just taking t0 square, omega 0 minus omega square, 1 minus gamma, 4, 1 plus gamma square, taking the square, right? So I think you are thinking that this will also become 1 plus gamma square, and this will cancel with this one. Is this what you are thinking? But to the proper ways, we have t0 square, omega 0 minus omega square, 1 minus gamma. So it's better to separate the real part and, sorry, the imaginary part. So we have this, right? So we need to take this mod square. So before that, one thing you can do, just separate out the real part of the exponent and the complex part. So real part will have 4 1 plus gamma square, and there is the exponential part which is minus I gamma. Yes, you can't cancel, you are right. So I'm just uh, showing a brief step like how you can achieve this. So you already have separated out, right? So that means you can now this part will be 1 when you take the mod square, right? Because it will give a IO gamma part, but this part it will give exponential t0 square omega 0 minus omega square by 2 1 plus gamma square. This is the way, one of the way that you can approach. Okay, so let us move to our last problem. Hmm. So it says consider a optical fiber with beta 2 is given, which is negative, which means it's a anomalous dispersion region. This is minus 20 picosecond square per kilometer. And nonlinear curve coefficient is given, and 2 is 2.6 into 10 to the minus 20. Effective core area is also given, which is 50 micrometers square. Now consider a chopped Gaussian pulse at lambda is 1550 nanometer is allowed to propagate through a fiber where both dispersion as well as the Kerr effect influence its evolution. So now instead of one, we have both, which is controlling the pulse evolution. And it is also given that the pulse size, the peak power is 100 milliwatt, T0 is 1 picosecond, chop parameter C is 2. So derive the nonlinear Schrodinger equation governed by the pulse propagation. So for the nonlinear Schrodinger equation, we have nothing but dose I, dose Z. So we have a term of both dispersion as well as the nonlinearity. So this is the dispersion term, this is the nonlinear term. So psi is the phase envelope if we recall, and T is the retarded time. In the B part, calculate the dispersion length and the nonlinear length, which is easy also, right? LD is nothing but T0 square by beta 2 mod, which is 1 picosecond square. Beta 2 is given 20 picosecond square per kilometer. So this will come 0.05 kilometer, and L and L. So this is 1 by gamma P0, which will be, so if you put the value, this will be effective K0 and 2 P0, and K0 is nothing but 2 pi over lambda. Lambda is 0 is given 50 nanometer. So just put the values. This is 10 to minus 12, 1550 nanometer, 2 pi, 2.6 into 10 to 1 minus 20 to 0. So this will come around 4.7 kilometers. So one thing you will notice here is the length for the nonlinearity, which is it is much greater than the length for dispersion. Okay, so that means if we have a fiber of let's say length L, which has a length comparable to LD. So this means that initially there will be dispersion effect. The dispersion effect will control, will dominate over the nonlinearity during the initial time period. But when the pulse propagates through a larger distance, the nonlinearity also comes into the picture. Okay, so initial the dominant behavior will be controlled by LD instead of LN. Okay, so for the C part, what is the expression for nonlinear phase shift at 1 kilometer? So nonlinear phase shift, this we already know the expression. It is gamma L psi 0 square. So gamma L, this is let us say P0 e to R minus T square by tau 0 square. So maximum value for this nonlinear phase will be gamma L P0. The peak value for power, length, and the nonlinear coefficient. So we have everything in our hand. So this is 10 to 3.1, which will come around 0.21 rad. Okay. So depending on the how the LD and LNL how they are different to each other, you can say which one of the effect will dominate. Let us say we have L much less than LNL, and we have a length which is also less than LD. So that means there won't be any effect of non-linearity as well as the dispersion in the medium. So the pulse will propagate undistorted for this case. But if you consider a case when L is approximately in the order of LD, but it is much less than LNL. So that means the dominant behavior will be the dispersion effect. There won't be any non-linear effect, which this will be there will be, but it is negligible. Okay. And if you have a case like this, where L is in the order of LNL, but it is less than LD, then non-linearity will dominate in that case. And if we both, so L is in the order of both LD and LL, then we can see the both effect, both the dispersion effect as well as the non-linearity effect. Okay, so this is what I wanted to cover for this week 12. I hope whatever I have discussed or the questions that has been solved during the live section, it is quite clear to you. If not, please feel free to ask the doubts. This is the last session of this course, Physics of Linear and Nonlinear Waveguide. So I hope the tutorial session is helpful to you. I tried to cover all the concept that has been taught during the course, uh, and all the best for the for your exam. For exam, I can suggest please go through the slides, the lecture content, as well as the weekly assignment that is being floated in the NPTEL side, as well as you can also try the tutorials problems. Okay, so this will help you to understand the concept much clearer. I have to ask one question. Yes, you can ask me. Okay, so transcendental equation, I don't think so. They will ask about, they will give any question that where the programming is required. Whatever is required, it will be the parameter will be given because it's not possible to do the programming in the question, right? In the exam. So from my side, whatever I know, it's not mandatory. It's not possible to do the programming in the exam. So they will give you sufficient information to find out the transcendental equation, what will be the values. Okay. Or otherwise, one thing you can also do because it's from the NPTEL side, you can raise your question in the group. Okay, so there is a group for this course, right? You can raise your question so that the uh, the person who is making the question, they will answer your questions, whatever. So if you have any other doubt regarding question, also you can ask in that group. They will promptly answer. Okay. Okay. So if you don't have any doubt, so I would like to thank you um, to the students who joined the session, who asked a doubt, and okay, so all the best for your exam. So, okay, so let me end the section. Goodbye, everyone.